thank you all for joining. It's very glad to see this high amount of interested people joining this webinar. My presentation will be about the emission and interaction of supraharmonics from electric vehicle chargers. And as Thijs already told, that's a topic I've been working on for almost 2 years already. So I hope that I can share some interesting results on that with you. I will first introduce very briefly something about supraharmonics. I think most of you also joined the sessions this morning and the other sessions yesterday, so maybe already have some thoughts already about it, but I will briefly introduce it. Then I will show some results from the supraharmonic emission of electric vehicles I obtained. I used various lab setups and also some field measurements for that to obtain the supraharmonic emission spectrum of electric vehicles. Then I will say something about propagation and secondary emission. I think this morning in the presentation from Angela, it was already noticed that it's very difficult to distinguish primary and secondary emission and what is actually the difference between them. So I will elaborate a bit more on that. And also I have some interesting results on supraharmonic interaction that is possible to occur. Was already mentioned in the presentation of Jan Meijer this morning, frequency beating. I will elaborate a bit more on that in a few moments. So very briefly to start, supraharmonics is the name of all waveform distortion between 2 and 150 kilohertz. Yeah, a bit arbitrary limit, but it is actually chosen such that the upper limit is equal to the traditional EMC standardization framework, and power quality always used to cover up to 2 or 2.4 kilohertz, depending on whether you're in European or American grids. But in between those two standardization frameworks, actually a lot is happening, and that's where supraharmonics are playing a role. The research on this topic remains very limited because, this has mainly to do with the lack of standardization, but also, it was not really causing any effects on the grid. So why would you investigate in something that's not doing anything? But by now we know that supraharmonics can have some very particular effects. I think a very famous example is the whistling high-pitched noise induction cooking plates can make when there is a supraharmonic distortion present in the voltage. Of course, very annoying. Another one is the excessive heating of capacitors. Capacitors are in all your electronic devices used as filter, and they heat up excessively, which can lead to reduced lifetime and even breakdown and failure of equipment. And also, electric vehicles can be distorted by the supraharmonic components present in the voltage, which makes them unable to charge or to cause any other problems. My research mainly focuses on electric vehicle chargers, but I think it's important to pay a little attention to the different type of chargers that there are already. At first, if you charge an electric vehicle, the most common way to do it is using the onboard charger. It's mostly limited in power due to weight and size restrictions inside the vehicle, and normally has ratings between 11 and 22 kilowatts, some a bit higher, some a bit lower, depending on the manufacturer. And with those chargers, it takes between 3 and 8 hours to charge your vehicle. So that's ideal to use overnight or when you're in the office. Another option to charge your electric vehicle is using an EV DC fast charger. At the moment, I think the Dutch company Fastnet offers up to 350 kilowatts, and with that, some vehicles can charge within 20 or 30 minutes up to 80%. So that's a very convenient way to charge your vehicle when you want to travel longer distances. Also, the public transport is becoming more electric. I think Amsterdam has the largest fleet of electric buses at the moment of Europe, in the area of the Schiphol airport. And if you charge an electric bus, you can either do that overnight as well in a depot, which powers between 50 and 150 kilowatts. And you have also some opportunity chargers that are placed on the route, so you can stop for 5 or 10 minutes at a station and charge with powers up to 600 kilowatts to add some extra range to the buses. And you can of course imagine that these large amount of powers will have a very high impact on the grid as well. Now, my research up till now focused on the onboard charges of electric vehicles, but my future plans and also part of my PhD are to also focus on the DC fast chargers and also the chargers used for the electric buses, so including the higher power ones. But to start with supraharmonics from electric vehicle chargers. This is a measurement result I show a lot because I think it's a very nice example of how supraharmonics look like. Because I think the most of you see a three-phase balanced system, more or less balanced three-phase current. But you can immediately see that there's something odd with this current. There's something on top of it. And in this case, that's a waveform with a frequency of about, I think, 10 kilohertz that's put on top of this current of the vehicle. And this is caused by the inverter of the electric vehicle. Now, if you want to know a bit more on what is actually going on inside this charging or with the signal, it's always better to look at the frequency domain instead of the time domain. And then it's very easy to distinguish the 10 kilohertz peak in this case. The vehicle was charging at about 20 ampere, and the supraharmonic component has values up to more than 1 ampere, so that's more than 5% of the fundamental. And that's really a lot. If you know the limits for harmonic components up to the 40th, I think this value is way less than the 5% we have here. So this is something that I think should be avoided. And if you take a look at the voltage, you also see that there's 1.2 volt present at 10 kilohertz as well, which means that all devices connected on the same feeder or close to this electric vehicle will also see this component in their voltage. Now, when you talk about supraharmonic emission, it's always difficult to distinguish where emission is coming from. So you need to distinguish between primary emission and secondary emission. Primary emission is emission coming from one device only, and that's only one single way to test it, and that's using a clean voltage source. But also that will not give you the most representative results because your impedance will be different in a practice, and also the whole grid characteristic will be different in practice. But anyhow, to determine primary emission, to see at what frequencies the vehicle is switching, or to make a harmonic fingerprint, low frequency behavior, it's very convenient to use a clean voltage source to analyze this kind of behavior. And of course, when you do this, you can play with the variables like the harmonic distortion in the voltage already present, or the charge speed of the vehicle. Anything can be controlled, and the effect on the emission of the vehicle can then be determined. In practice, this is a bit different. So in this example, we have 4 electric vehicles. And now the emission from vehicle 1, when we connect it to this small grid, is not only going back into the grid, but also a part of its emission will be absorbed by the second vehicle, even the third vehicle and the fourth vehicle. And the ratio will depend on the impedances of those vehicles and all other devices connected inside the grid. Now the same will happen for the second vehicle. Also, part will flow back into the grid. Part is absorbed by the other vehicles. Same for the third and also for the fourth vehicle. And now if we are going to measure at this point or at any point in this small grid, you will always see the addition of the supraharmonic components from all these devices with a certain ratio between them. And then it's very difficult to distinguish what emission is coming from who and who is responsible and just accountable for this emission. And of course, in the field, there are many more uncontrollable parameters. The background distortion and the voltage will always be different, and you do not know exactly how this grid will look like, which makes it very difficult to predict what will be the behavior of an electric vehicle in the supraharmonic domain in practice. Now here's a little schematic which shows very simple the difference between primary and secondary emission. And it's a very simplified schematic, but it's good to understand the difference between them. So let's say one device is here depicted as a current source, in this case a supraharmonic current source. So let's pick a supraharmonic current which is injected here. then a part of this current will be absorbed by its internal impedance, Z1, and a part will be flowing out of the device. So this is the external emission of device 1, or called the primary emission. A part of this emission will go back into the grid impedance, and a part will flow into the neighboring impedances of other devices, in this case, the internal impedance of device 2. And now if you are going to measure at this point, you will see the emission coming from the constant current source of device 2, the supraharmonic current source, but also the component coming from the first one, I1.2, it is called. So here you can see it's very difficult to distinguish primary and secondary emission. Now, to do some experiments with these larger amounts of electric vehicles and combinations of them, I use two different setups. At first, at the ElaadNL test lab here in Arnhem, we have the ability to charge vehicles, to supply them with a clean voltage source, and to really see what this vehicle is doing and what the emission is coming from this vehicle. On the second hand, I did some experiments at the Joint Research Center Smart Grid Interoperability Lab in Petten. And this lab, I will show a schematic of it later on, allows us to charge multiple vehicles at the same time, and also to operate either as microgrid or connected to the public grid. And the last one is a very unique feature. This is a small schematic of the grid at the GSC. This one depicts the public grid connection, so that's just a low voltage cable going to a transformer somewhere. But there's also a battery storage capability and solar PV panels on the roof. And you see here as a switch depicted, which means that we can also switch off the public grid, or not really switch off, but disconnect the public grid, such that the lab will only be supplied by the battery and the solar PV inverters. And this allowed me to see the influence of, taking away this impedance and also taking away a large part of the background impedance or background distortion from the grid. And it has sufficient connection capacity to connect 3 or even 4 vehicles in parallel, and some other equipment that was available in the lab, some LED lights and some computers. Now, another schematic is similar as the previous one, showing harmonic propagation. I already showed this a bit, but if you have a harmonic current source of one device with its internal impedance, it's in this simple schematic very easy to determine the part of the emission that goes into a second device or a third device, or this could be the inverter of a PV panel, or this could be the grid in this case. So the supraharmonic emission will split into all different devices depending on their impedances, which should in fact be question marks because we do not really know what the impedances are. Now, the first interesting result. I tested 9 very common electric vehicles in the Netherlands. I think by the end of 2018, they covered 95% of the available electric vehicles in the Netherlands, so that's very representative of what's on the road over here. And I think the most important conclusion is that in this case 8 out of 9 electric vehicles are a source of supraharmonic currents, and some a bit more than others, some quite low and others a bit higher. But also something important to notice is that I think 5 or 6 out of them have supraharmonic components or supraharmonic switching within their hearing range. So this could lead to audible noise, which humans can hear, which is extra annoying, of course, next to the earlier mentioned effects the supraharmonics can have. Another example, a quite odd one, I think, because the most electric vehicles I tested at a very narrow band peak at one specific frequency, but this one showed a more broadband frequency spectrum. And some further analysis in the time frequency domain showed that, in fact, it's not using constantly the completely broadband spectrum, but that the frequency is actually changing with more or less the frequency of the grid connection between 45 and 50 kilohertz. And we do not know exactly why, but I think one of the reasons could be that by using switching patterns like this, the peak emission could be reduced. So by making the spectrum more broad, the peak value could be reduced. So this is maybe a way of the manufacturer to avoid exceeding overcurrent limit that could be there in the future. Now, supraharmonic propagation tests I did in the lab, also some interesting results. I've chosen to use the time frequency plot as well over here, because then it's easier to determine or to compare the results on the background emission as well. You do not really see any difference between this part and this part, where we added the second electric vehicle, and that's actually very very nice to see, because this was the only vehicle without any emission. That was the only one on the list that didn't show any supraharmonic emission, but it seemed that it is also not absorbing any part of the emission emitted from the first electric vehicle, because this is measured at the first electric vehicle. And yes, the electric vehicle was charging. We measured that as well, of course, but somehow they were able to have no supraharmonic distortion at all. And here we added the third vehicle, and you see that the peaks at 10, 20, 30 kilohertz intensify, and that has to do with the fact that this vehicle is in fact of the same type as the first one, the red one, resulting in another additional effect, frequency beating. I will discuss a bit more about that in the future. So that's an interesting result. The second vehicles, this one, the blue one, it's called the blue one, didn't really show any emission when charging at 16 amps, so the highest level it could take. But when we started to lower the fundamental current the vehicle was taking, so when reducing the charge speed to 14 amp or to 12 amp or even lower, which is normally done also when applying smart charging to a vehicle, we saw this broadband emission spectrum appearing. And that's something interesting, because normally vehicles or devices are always tested at that nominal power or the maximum power, but electric vehicles are made to operate at all different current capacities. So I think an important conclusion from this one is that the electric vehicles should not only be tested at their fundamental or maximum current, but also at lower ones, because that will in practice maybe more often be used. Now the last result, adding the red vehicle, you see that the part of the emission at 10 kilohertz was absorbed by this one, resulting in secondary emission coming from the red one, measured at the blue one, at those frequencies. So very shortly, the results we already discussed. Of those four vehicles, it seemed that the first, the red one and the blue one have the same switching frequency, and they absorb large parts of the emission from each other, and also a large part is going back into the grid. The second vehicle, no emission, no absorption at all, and the fourth vehicle absorbs only a small part of the emission from the first two vehicles, and its own emission is mainly also absorbed by the other vehicles, and a small part flowing back into the grid. And the main difference between those vehicles is the switching frequency. So I think I had not enough information to really conclude anything about the grid impedance, but an estimate could be made of the impedance of the devices, the vehicles, and the grid impedance at this case. But I think it would be interesting as well to maybe measure the grid impedance to make a better estimate of it, and to also see the effect of changing the grid impedance on the emission at different frequencies. Supraharmonic interaction. During the measurements I did, I investigated two different kinds of interaction that could possibly occur. The first one is frequency beating. I already discussed this morning very briefly, and another supraharmonic interaction, intermodulation, and I will show a bit more about that. So as already mentioned, we have two identical electric vehicles, but by saying identical, they are not always perfectly identical, meaning that they will always have a little impurity in components or whatever, and that's why they are not always switching at exactly the same frequency. So in this case, the first vehicle had a switching frequency that's called frequency A, and the second one, frequency B, which is frequency A plus a little bit. And some very interesting effect happened. It was immediately visible that the waveform started to have a certain sort of beating effect, that the amplitude or the supraharmonic component intensifies and reduces again with a certain period. So, of course, I analyzed this a bit further. And in this graph, you can see the fundamental or RMS currents taken by the vehicle, and I extracted the supraharmonic component around 10 kilohertz. And here you can see very easily that the supraharmonic component has certain periodical behavior. And if you count the number of periods, you will see that this frequency will have a period of 2.4 or frequency of 2.4 hertz. And that has to do with the small difference in switching frequencies between those two electric vehicles. Now, if I then take a look at the spectrogram, the time frequency analysis, it's also visible that this is the component at 10 kilohertz, which is changing its intensity every 2.4 times a second. And this effect happens when you add 2 electric vehicles, but also when you have 3 of them or 4, but it already happens at 2. And this means that the peak value of the emission is really increasing compared to the value the first vehicle had. So this is something to further investigate. And I'm mainly saying this because at this particular charging location, multiple times a week and even during the charging session that we did, there is dual current protection devices which are there to protect you against earthing faults. They tripped repeatedly during the test. There were no leakage currents measured, but we highly suspect this frequency beating compared or next to the high supraharmonic component of the electric vehicles to have something to do with it. But yeah, we need to further research this to really tell something about it, if this is really something old with this particular RCDs, or that's something that could affect all RCDs. Because false tripping is of course annoying, the electricity went out, but there are also some papers showing that the RCDs could possibly get blinded by those supraharmonic components, and that's of course very dangerous, because then they are not switching when they should. Another comparable supraharmonic interaction is the intermodulation distortion. In the previous example, we saw a very small difference between switching frequencies of a couple hertz or maybe 10 of them. But in this case, there's an intermodulation effect caused by 2 components, one at 60 kilohertz and one at 56. So that's a quite large difference compared to the last one, 4 kilohertz, which is resulting in additional second, third, and fifth order components at those distinct frequencies. And those frequencies all have a certain relation with those fundamentals, because they are either the difference of them, second order, the difference of the multiples of them. And this resulted in a very polluted spectrum, such to say. And originally, there were only 2 components. And this is also, I think, a very interesting effect to further investigate. I'm not really sure what the additional effects of this will be on the grid or on the equipment, but what I can conclude is that those 2 high components resulted in a lot of additional components, which are of course highly unwanted. Now, already at the end of my presentation, I think to conclude, we saw very interesting things. At first, the measurements I did on the different electric vehicles, it was concluded that 8 out of 9 are a source of electric or supraharmonic components, and that most have supraharmonic components within the human hearing range. So that's something that really should be considered. Propagation depends really on the grid impedance and on the device impedance. Taking away the grid connection resulted in different emission from the electric vehicles, and also, of course, will change the impedance of the PV and the battery inverters. But as mentioned, it is very difficult to determine the high frequency impedance of a device by just measuring or looking at it, because this possibly is also affected by the operation stage or the type of grid where it is in. We looked at supraharmonic interaction. The frequency beating and intermodulation distortion are two important examples of this, and I think those effects will also be occurring with other devices that have very distinct or very high supraharmonic switching frequencies close to each other, and this really needs some further research. The RCD operation is possibly affected. This could be a serious safety issue, so I think future standardization should really look into that, and also tests on RCDs, also the high immunity ones, should not only look at the whole complete frequency spectrum, but also at the low frequency behavior like the beating effects, because those could play a role in the operation of those. And I think one of the most important conclusions of today and yesterday is that mainly in the field of supraharmonics, more research is needed to determine the propagation of supraharmonics to the kids, to see what emission of individual devices is and how this could be affected. So I really would like to contribute to this, and I'm also, I of course am contributing to this, and I would like to encourage everyone working in the field and still looking for an interesting topic to work on to consider working on supraharmonics, because this is a topic that really is under attention now for a certain important reason. And with that, I would like to end my presentation. Thank you all for listening, and now some time for questions.
Okay, excellent, Tim. Thank you for your presentation. Well, we did get some questions, so let's start. Let's go over them. First one from Miriam Niamey. It's a hard name to pronounce, from the Newcastle University. She's asking what kind of equipment is required to collect data to understand the impact of supraharmonics from electric vehicles.
Yeah, always when considering supraharmonics, a lot of devices do only consider the voltage. They are not measuring the voltage and the current. But I think to really determine effect on the grid and to really understand emission and interaction, you always want to see supraharmonic voltages and currents. So you need a device that is able to capture that complete spectrum up to 150 kilohertz or maybe even higher for both the voltage and current. And I noticed myself, because we have been looking for equipment for the test lab, of course, that there are very little manufacturers that really have devices with those capabilities, especially for field testing, because you do not want to carry a bulky computer measuring equipment device into the field. It's not very practical. But I would say, do not, if you really want to understand what's going on, do not only consider looking at the supraharmonic voltages, but also always take into account the currents as well. I think that's the most important aspect.
Excellent. So let's go to another question from Thomas van der Wart. It's a long question. So with the negative effects that these supraharmonics may cause, an operator of charging stations would want to understand which type of vehicle may cause these kind of issues. How do you view your role as a researcher to inform the market about these specific findings on specific vehicles that are driving around in the European Union?
Yeah, that's a good question indeed. For research, it's not really needed to know what vehicle is really causing the problem. I'm collecting all data and using it to have a representative overview of what is going on in the field. But I understand that for charge point operators, they would like to have more information on what individual vehicles are doing. But I'm not allowed to give this information because we are testing the vehicles and we are signing NDAs and things, so we cannot share those results with you. But what we can do is that we inform both the manufacturers and also the different parties that are playing in the field about the effects that could occur. And that's not really a matter of what vehicle is causing them, but if you are ready for the effects and you know how to counteract them or to mitigate them, I think that's a good point to start.
Excellent. I hope that answers his question. I believe so. Let me see. We've got another question from Naimi Bohari. The RCDs used, what type were these RCDs? So are they type A or type B?
Now, in the Netherlands, it's required to have always type B RCDs in the charging stations. So these RCDs were also of type B. And I'm not sure, but I even think they were of the high immunity classification. High immunity is a bit, I'm a bit playing with that because manufacturers used to put the stamp high immunity on RCDs, but it's not really transparent what that means. What does high immunity mean? It's always a difference between different manufacturers. But yes, it's also always type B.
Okay, excellent. That's a clear answer. Let me see. We've got a nice one from Kevin Lorenzo. Hello, Tim. Nice presentation. So yeah, you did nice. From our experience, it seems that supraharmonics mostly stay inside the installation where they are generated and circulate between the different appliances, on the contrary to harmonic currents, which are usually mainly going to the grid. Is this something you had occasion to observe as well?
Yeah, I already showed, of course, with some results that for some vehicles it stayed within the installation and was absorbed very locally. But I know for a large parking lot with, I think, 15 different chargers, I did some measurements, and that also seemed that the current between the electric vehicles was quite distorted. You could see all individual switching components, but the current going back into the grid was indeed quite clean. I have to say, in that case, there was a dedicated transformer plus dedicated cable going to this charging station, so that might play a role in not absorbing those supraharmonic components by the grid. But I think in a more representative situation, like a neighborhood with a lot of houses, that the supraharmonic currents are not necessarily staying within the installation of the household. Because if the neighbor has a battery installation or an EV or PV panels or some other device with low impedance, those will definitely propagate to the other households and the other connected houses on that feeder as well. So I think indeed that for most lab experiments, it will show that the supraharmonic will stay within the installation, but I do not know myself, but I expect this to be different in practice.
Yeah, it all has to do with these different impedances, right? Also on the different frequencies. Also something we still want to investigate. Well, we have another question. We still have some time, right? From Sharmista. If you have 10 similar type of EVs connected, does the pollution increase 10 times? Or what's your observation? Frequency beating. Frequency beats can increase the band of frequency and reduce the peak, right? That's what she's asking.
Yes, for frequency beating, when you have two electric vehicles, the peaks will be increased. It is not really adding, because the different thing of supraharmonics is that, you cannot really say anything about phase angle like you do with normal harmonics, because supraharmonics are not really related to the fundamental frequency of the grid. So there's no such thing as a phase angle, and also that makes it very difficult to determine if it will add or if it will subtract from each other. But I know from some experiments that were done that it will at first increase, not like 2 times, 3 times, 4 times, but a bit less. And then depending on the grid impedance or on the impedance of other devices, it could even decrease later on. And there were some experiments by Angela from Luleå in Sweden. She had a presentation this morning. I think she really showed some interesting results on that.
Okay, excellent. Let me just select one final question and then we'll continue on. Here's a question from Stefan Hell, and he's asking if you saw an effect in different type of chargers. So if you have an 11 kilowatts or 3.7 kilowatts or 22 kilowatt charger, if there were different supraharmonic effects.
Yeah, I think the most vehicles I tested were either 11 or 22 kilowatts, so that's difficult to compare. What I do know is that if you take a charger for, let's say, 11 kilowatts, and if you reduce the power, so like I showed in some results, that the behavior changed. So I suspect that for the lower power chargers, the effects will definitely be different because the sizing of components will be different, and also the switching frequency. But I did not do experiments on that particularly. But I hope to see something similar or some more information on that when testing the high power DC chargers to see if they behave similar or very different from the normal onboard chargers.